Okay? Okay. Okay, so let's start the second half of the lecture. And it's a continuation of the first part. I'm just going to talk a little bit more about the local essential tree and some So this picture I already described. It's how the different ways of parallelizing using MPI, and I forgot to mention what HOT is. So it says Morton HOT and Hilbert HOT. That is abbreviation of hashed oct tree. So hashed is because you use I'm just trying to fix the. Okay, so the hashed oct tree is called a hashed oct tree because when you use the Morton or Hilbert index, it creates an oct tree in 3D. And these indices, Morton index or Hilbert index, these keys are called hash keys. You can think of it as a hash. So if you know what a hash function is, you can view Morton or Hilbert keys as a hash key. Okay, so now we compare the performance of these two codes. So this is actually looking at the numbers of when you run these codes and what happens. So what I'm plotting here is when you increase the number of MPI processes. So this one has just one rank. It's running in serial. And then this one is running on 2 nodes. And this is 4 processes, 8 processes, 16, and goes up to 1,000 MPI processes. And every time I increase the number of processes, I increase the total n. The problem size is increased to like 2 times, 4 times, 8 times. So what happens if I do that is each partition should have a constant number of work to do. Because in total, the work is order n. So FMM is an order n method. So when I increase n, the total workload increases n. And so if the number of processes is p, and I'm increasing n to be proportional with p in total, then n over p, which is the work that each process does, should be constant. So the timing should be constant. This is called weak scaling. So there's strong scaling and weak scaling. Strong scaling is when you keep the global problem size constant and use more processes, MPI processes, in parallel to do that. In that case, the timing should shrink proportional to the number of processes you use. But if you increase the problem size proportional to the number of parallel nodes you use, then the timing should remain constant. So this is the kind of test I'm doing here. And so you see that I think this red part here is mostly the tree traversal time, which is the M2L and P2P kernels. So that was, I showed you in the first lecture that was the most expensive part of the calculation anyway. And it's still the same thing here. And the communication parts that you see, and it should be dark blue, all these communication of LET, communication of the cells, and communication of the partition. That part remains somewhat small throughout the calculation. But so that's if you use this Morton hashed oct tree. But if you use this new orthogonal recursive bisection that I thought was a good idea, it actually turned out it's not such a good idea. So what happened was not only did the communication increase here, but what happened was the traversal time increased. So here it's always like lower than 35. But here it starts out like at 35, but then it goes up and it goes up. And why is it going up and down? So if you move this legend here, it's probably going up for 1, 2, and 4. And then again 8, 16, and 32. So one key feature here is that this is a oct tree. So this is in 3D. So every time I go to a power of 8, it's chopping the box into 8 square boxes. But while it's at 2 or 4, it's creating rectangular boxes. Okay, so at 16, it's chopping the domain again into like a rectangular x direction. And then at 32, it does it in the y direction. So now you have, instead of these rectangular plates, you have like a rectangular, long, thin, like a tube-like domain at 32. And then at 64, it becomes square again. So every time the domain becomes elongated, the amount of communication seems to increase. And this is because even though I tried to avoid the alignment issue with the underlying tree and this partition, I wasn't completely able to avoid the growth of the interaction list. So what happened was the interaction list size grew because I had like not so ideal shapes of these boxes. So I had to grab more boxes from far away, and this number sort of grew. So even though it looked like a nice idea that you could just graft the root nodes of the subtree to the global tree, it turned out that the interaction list size grows, and then the M2L calculation takes longer and longer. So then that was one thing. Now this shows the amount of communication that's being done in sort of a matrix form. So if you plot all the nodes in your communication, so say that you had a very large calculation and you were using 1,000 MPI processes, then those 1,000 MPI processes talk to each other in a certain way, right? And then if you create a 1,000 by 1,000 matrix that represents in color which ones are talking to each other, then if there's no communication between the two MPI processes, it shows black. But then if there's a little bit of communication, it shows in like blue, and then in green, and then red, and so on. So you can see, no, sorry, I think blue is more communication. Red is, and this dark brown is not so much communication. And so at the bottom level, it sends a lot of data. So you can see a lot of blue lines. Like I mentioned here, the amount of nodes it communicates with is not so large, but it sends a lot of data per node. And then at the larger levels, the amount of communication it's doing is small, but it sends to many other processes that were sort of not being communicated here. So you can actually see that the dark spots, you see that like these dark black boxes here, here, and here, they're actually filled in on this side. So it's actually complementing the data that was not sent in these levels. You can see that this part here is actually sending the data that wasn't being sent in these 4 slides. And if you look closer, you can actually, so if you add all these colors, then it should fill the whole domain, because someone needs to send, from somewhere. There's no 2 nodes that don't need each other's information at all. It at least needs something at the higher level of the tree. You can't get away with no communication between the 2 nodes. And so this color map represents the communication pattern, and people in like high performance computing like to look at these patterns and see, for example, if you did fast Fourier transform, FFT, the communication pattern would look like everything is sending a lot of data to everything, like equal amount of data. The interesting thing about this method is that the further and further away you go, it sends less and less data, unlike the FFT, which sends equal amount of data regardless of how far you are. And so, yep.
Sorry, just curiously, how do you generate these graphs? By using some kind of tool?
There's a tool, yes. I forgot the name, but there is a tool that generates this color map. Yes.
So that's a real thing, not conceptually.
Yeah.
Okay. Cool.
I think it was called Tau. TAU.
Oh,
Yeah,
okay.
Tau. Okay, so now This is about the communication complexity. So complexity is, usually discussed in terms of the computational complexity. So we discussed that the direct n-body method, which does everything against everything, is order n squared. And that the FMM changes this to order n. But what about the amount of communication it needs to do? So this complexity might be a more difficult problem. But it's more important because the communication eventually becomes the bottleneck. And so if you had P processes, so if you had P parallel processes, how much data does the algorithm have to send? And for the FMM, it's of the order log P. So it depends on the process, but if you look, in total, the per process amount of communication that you're doing is of log P. And then if you think of the cost of data movement, then it's becoming more and more expensive. So this is in time, in 2002, 2005, 2008, and 2011. The cost for sending, so this blue line is dollars per megaflop, and this red line is dollars per megabyte. So the cost, the actual cost in dollars for sending bytes is not decreasing too much. So it's getting cheaper and cheaper to do flops. So if you had like a GPU, it can do a lot of flops, and you don't have to pay so much to get those flops. But if you want to send with MPI through the network some communication, or if you had to load data from your memory to the cache, then this kind of data movement is not becoming that much cheaper. Of course, it's becoming a little bit cheaper in time, so it's not like there's no advancement. But data movement cost is a more difficult problem to solve. And so when people are designing machines for exascale, they are worried that the cost of sending data will become, so if you extrapolate this to 2021, then the cost of sending data becomes the true bottleneck. And so when you're talking about internode communication, there's no like breakthrough technology that's going to give you, there's like incremental advances like Intel's OmniPath, and these things are giving you like an incremental advancement, but still there's no like a complete breakthrough technology that will change the slope of this line. So then, since I'm talking about MPI, I thought I should discuss these issues. And so, well, again, this is not showing the whole slide. Okay, so this is the same complexity analysis that I showed earlier. This is just a bit of history. So in 1998, the total communication complexity was thought to be this much. And in 2009, it improved to this much. But now we have this log p plus n over p to the 2/3. I mentioned in my previous slide how you get this number. But this is like the different estimates for the amount of communication you have to do for the MPI code. Also, you can model the communication time it takes on these different machines by measuring latency is the amount of time it takes to initiate and terminate communication, not necessarily the time that's proportional to the amount of data it's sending, but even if you're sending very small data, there's a constant amount of time it takes to start the communication. So this part is called the latency of communication. And the inverse bandwidth is roughly the time it takes to send a given amount of data. So if you had like 10 megabytes of data, then if the inverse bandwidth is large, it's like this is like the inverse of the bandwidth. if this number, so if the bandwidth is large, this number is small. And so it would take smaller amount of time to send the same amount of data. And then you have also, since the network I discussed for large computers is not just one switch connecting all the nodes. It's just like multiple switches and connecting in like more than 3 dimensions or like connected more densely. So you hop through the network. So in terms of network topology, we can count the distance between the two furthest nodes having a given number of hops. So you need to hop through 5 times the network to reach a far node. So there's a delay per hop that we need to add. And then the message size, number of hops, these numbers, you can add to the equation. These first 3 numbers are the parameters of the machine. So if you're given a machine like Cray XC40, Blue Gene Q, or Cray XK7, these numbers are determined by the machine. And these numbers, well, the bandwidth is also determined by the machine, but these numbers here, N, H, and C, these things you can actually control yourself. So you can actually, sort of decide who to communicate by considering these numbers of hops. You can also decide the type of communication you're going to do and change the message size. This is more of an algorithmic issue. And also the number of cores is determined by the machine. So if you sort of keep adding more and more terms to this equation, you can get more and more accurate estimates. And so the black line is the actual measurement. And it shows that these, when you add all the terms, like this purple line, matches quite well with the actual measurements. The error bars is the load imbalance between the different MPI processes. And so if it fits inside this bar, that means we did quite a good job predicting the performance. Yep.
I don't really see why the number of cores C affect the communication.
So it appears in this term here where you have like a multi-core penalty for the communication. So say that you had like 6 cores on your machine, and all 6 of them ran an MPI process. And then that sort of creates a congestion because instead of one person sending from the network, it has 6 MPI processes trying to communicate. So you could, the bandwidth is shared among the cores. So this sharing of the bandwidth is usually what needs to be considered. So yeah, well, I guess it's being related to the number of hops in this case. But yeah, so.
And also related to latency in the second model.
Oh yes, so yes, indirectly, if you have more cores communicating, then it could it could result in more latency per core.
Sorry, just another quick question. So in 3 figures, so the label is that the label of 8 and 9?
Oh yeah. This is so yeah. Sorry, I didn't mention. So if you had a tree that is like 9 levels deep, then usually the communication happens from like below level 3, and these represent the time it takes. It's not necessarily the amount of data it's sending, but it's the time it's taking to do the communication at every level. So in this case, we sort of synchronized and measured at each level the communication separately. So it's not how you usually do the communication in FMM, but we wanted to see the effect of, because so at the coarser levels, at the lower numbers of levels, you are communicating with things that are further away in the network, but sending less data. So we wanted to see how that changes on these different machines. And we see actually quite a difference. So on the Blue Gene, to send to far away is not a problem. It's connected with a five-dimensional torus network topology. So sending to far away is not such a problem for this one. But on Titan, sending to far away was not, it had this performance hit. So these things are things you need to worry about when you run on very big machines. And finally, this is final performance you can get for strong and weak scalability of FMM on a Cray XC40 machine called Shaheen 2. And this is the number of cores it used. And this one is the weak scaling test. So if you remember the definition, this keeps the it keeps the local number of the problem size constant, and it grows the total problem size proportional to the amount of parallel processes. And this is, so yeah, it says 100 million n per node. So it's a very big calculation, and it's using many, many nodes, and each of them is calculating this much. This one is calculating 300 million in total, and so when it uses more and more, it's using less and less time, but just so that you can see the colors, because if I just plotted the time, you wouldn't be able to see anything here. So I just multiplied the time by the number of cores so that you can see the color bars. And so although this is showing like it's taking 700 seconds, it's actually 700 divided by 32,000, which is like 22 milliseconds. So this is a very, very fast calculation that I'm doing. So 300 million n is being calculated in 22 milliseconds. And you can see that the ratio of the communication when you do the strong scaling tests grows. And also this other part that was negligible in the previous calculations and also somewhat negligible in the weak scaling tests becomes quite large. And other is just something that's not the tree construction and not the traversal. So it's the other parts. So insignificant parts of the code start to show when your total running time is 22 milliseconds for 300 million points. And so you need to worry about different things when you reach different levels of parallelism. But in total, this is like the current very large scale calculations that you can do with FMM. And to do this, you need to know how to program in MPI. But once you do that, and once you do what I explained earlier this morning today, then you can run codes at very, very large scale. And so this is the effect of being able to do MPI. You can run on very, very large systems. So now I'm going to discuss a little bit about GPU programming. So for those of you who are not familiar with what a GPU is, it's originally it's the part of your computer that draws the graphics on your screen. And it was not originally used for programming, like scientific computing. It was used for graphics and people who play like 3D games. So all the gamer group community had a strong need for very high resolution rendering of very high definition graphics. And this kind of computation requires a specific kind of processor, which is each bit on your screen is rendered by a separate core. And so if you have like a 1000 by, like 1K screen, then each of those dots can be processed separately. So it's a very, very parallel calculation. And so GPUs evolved into this very, very large multi-core, many-core kind of architecture. And so a typical GPU will have more than 1,000 cores. If you can utilize all these cores, you can get a much faster and much more efficient, energy-efficient calculation because you're sort of throwing away all these energy-hungry parts of the CPU and just doing very simple usage of transistors and a lot of them just to increase the throughput. So, but it's very difficult to program your code so that it uses 1,000 cores. So this is sort of the difficulty the underlying difficulty in GPU programming is to exhaust so many cores. It's not just that you have to write in a new language, but it's that you have to change your algorithm so that it actually uses 1,000 cores. So nowadays, it's not just GPUs. Intel also has this new coprocessor called Xeon Phi. Maybe you've seen it. It's like the blue version of a GPU. It looks blue, and you can plug it into your motherboard through the PCI Express bus. So it looks like a GPU from Intel. And for those, it also has like many cores. It's like 60-something cores. And if you have so many cores, it's already difficult to program in a way. And it has to do with the thing I mentioned for OpenMP, the shared memory issue, the shared data issue, and how to keep all the cores and its caches coherent. And so those issues are handled in different ways for the Intel one and the NVIDIA GPU. But what I'm going to describe here is a little bit of how a GPU program will look like. So I'm just going to give you an example for this direct n-body kernel. So this one calculates, this is a 3D one, so it has x, y, and z. And it calculates the interaction of everything against everything. And it calculates not only the potential that we're calculating in all the examples, but it also calculates its gradient, the acceleration. So if you calculate this thing in OpenMP, like I mentioned, that's still parallel, and you can run it on a multi-core processor, and it will look like this. So this is the whole code. And you just need to add this pragma MP parallel 4. And so this code, if you write it on a GPU, it will look like this. So what changed? These parts don't change. So basically, CUDA is the language used to program NVIDIA GPUs. And if you write C code, then CUDA is mostly C. So all the float definition, function definitions, and the loops, integer. So the way you write your code is basically same as C. The only different parts are the index of your loop first changes. Well, so the outer loop index changed. The inner loop index is still the same. It's from J going from 0 to some number. But it changed. This n changed too. And so, first of all, you now have to deal with a unique index that is different. So when you're running in CUDA, you don't loop over from I, 0 to n, because this will create a serial calculation. It will just do things sequentially. When you want to do things in parallel, what you want to do is, so the GPU runs like this. So it has many threads that I mentioned. This is like an OpenMP thread, but you have many of them which are grouped into a block. So this is called a thread block. And then you have a grid of thread blocks. So you have many of these thread blocks running on the GPU. And when I said GPUs are difficult because you need to program how to run on 1,000 cores, they have a model of running on 1,000 cores in these blocks and grids. So each thread will be grouped into units of 32 called a warp. And you can have like 4 or 8 or 16 warps in this thread block. And then you can have many thread blocks, and these will swap in and out inside during your calculation, and you can't really control that. And it will automatically fill in the 1,000 cores by swapping in and out these thread blocks. So you can think of this model as sort of the GPU model of how to utilize all the 1,000 cores. And so each of these this block index.x and thread index.x correspond to the index of which one of these threads you are running. So thread index is a number from like 0 to, say that if you had 128 threads per block, it's a number from 0 to 127 that goes in here automatically. You can't control this. It will just, inside your code, you will have a number assigned to you that is from 0 to 127. And so this threads here, you set to 128. This is something you can control. So if you set this threads to 128, this will return a number from 0 to 127. If you set this to 64, this will return a number between 0 and 63. And this block index is then the index of this guy here. So you have many of these blocks. So you can have the block index representing which block you're calculating. So if you write here I, the total number of threads you're processing is block index time, the total number of blocks times the number of threads. And by assigning this, you calculate a unique index for each thread inside the block and through all the grids. So it's like looping over all of these calculations, except all of this will be running at the same time. If you have 1,000 cores, and if n was 1,000, all the cores will be calculating for a different I at the same time. So once you determine I, then you know which xi you're dealing with. So you load that xi, and each of these xi's are different for each of these threads. They're calculating a different xi. Everyone is calculating for a different xi, but for the same xj. So now, what I'm doing here, so this is kind of the special part of GPU programming here. Instead of me going, I'm going to loop from j equals 0 to n, like I'm doing here, I create two loops. So one is I'm chopping this into a few blocks that go from 0 to n divided by number of threads. Okay? And then I am taking x, y, and z, and m, which I'm directly loading here, and instead I am loading the appropriate parts to xj, yj, zj, and mj. And this xj, yj, zj, and mj I've defined here with a special type. It's not just a float. It has this thing called shared. And GPUs have like a controllable cache, except, GPUs don't have a cache, a proper cache, but, they have a L1 cache, but they don't have like the same cache hierarchy that you do in CPUs. Instead, you have this thing called shared memory, which is like you can access very fast, but the size is not so big. So you can't load the whole x, y, and z into shared memory. You can only load a small part of it. So this is why I'm doing this in blocks. I'm looping over this in units of threads, and if the number of threads is 128, I'm loading 128 numbers at again and again, and I'm processing the 128 that I've loaded here in this loop from 0 to 128. So I'm doing everything in 128 at a time, but utilizing this shared memory. So the access to xj, yj, zj, and mj are very fast once you do this load. So this part, you're accessing x, y, z, and m, and these numbers are defined in the global memory. And it takes like 400 clock cycles to access these numbers here. But these ones can be accessed in like 20 clock cycles. So it's much faster in terms of the clock cycles to access what's in shared memory. So you load once, and then you don't touch these for a long time. You just keep accessing xj, yj, and zj, and then just keep calculating from the fast memory. So you load, and then you just use from what's loaded. And so this model you can also use to optimize cache in your CPU, but I'll show in the next slide what optimized CPU code looks like. And it's more ugly than actually the CUDA code. So CUDA is actually a good compromise between a highly optimized code and one that's readable. So this is still somewhat readable, and it's very explicit on what it's putting in the fast memory. So in that sense, it's a very well balanced parallel programming paradigm for many, many cores. And so some people say CUDA looks, programming on GPUs is very difficult, but the lines of code has not grown, even twice. Now, I'm going to show you what highly optimized CPU, not GPU, but just normal CPU, but highly optimized code looks like. So this I don't intend you to read this, but it's doing the same operation, but it's using all these SIMD intrinsics that I described to you. And also, it's trying to optimize the cache usage by doing something similar to the shared memory usage that I described earlier. So it's loading in chunks at a time, and it's also loading so that it can optimize the SIMD operators. And so because each of the additions and subtractions need to be written by those intrinsic operations. So just to add, you need to write like add ps or something, like load, and even to load numbers, you need to do load. So this is like very close to assembly language. So there's a direct correspondence between these SIMD intrinsic instructions and a specific assembly operation. So of course, if you code in assembly language, which is like the lower level of languages which you can code in for CPUs, then it will look like this. It's very long. So, but this is very fast. If you actually run this code, maybe I can just send you an example, load it to the Google Drive. See how fast your code will become when you code it like this. And it actually becomes like 10 times faster, but it's very ugly. And once you do this, it's very difficult for you to change your code. For example, if you wanted to do a different kind of calculation, if it's like this, you feel like doing it. But if your code looks like this, you don't want to touch it anymore. So you need to really try to optimize not too early in your development stage. So do this when you're done with everything and you feel like you're finished with your algorithmic improvements, and then you can do something like this. But otherwise, it's not recommended to do this kind of optimization early on in your development. But I'm just showing this to you because some people say programming on GPUs is difficult, but that's because you're comparing with not so optimized CPU code. If you optimize your CPU code, it will look more ugly than your optimized CUDA code, most often. So it's just saying, for people who have never optimized the CPU code, GPU programming may look a little bit difficult, but GPU programming is just like halfway between heavily optimized CPU and a not optimized CPU code. So this is just an example of how to program. This is actually a running GPU kernel. So if you code this and then call this GPU kernel from your main code, then this will actually run. So it's actually real code that I'm showing here. And so you can actually run both of these in the tests. But do we have access to GPUs here? Okay, so potentially we could run in the hands-on session some GPU kernel like this, if we have time. Okay, so now maybe we can move to the hands-on, so we can cover more in the hands-on session. So maybe we can have an early break now and have a longer hands-on session. So let's have a break until 11, and then have a longer yeah, have a longer hands-on session today. So we can do more parallel programming. Yep.